Hello and welcome back to Engineers Olympiad. We're on to the second chapter of the Geotechnical Engineering, that is the weight-volume relationships. We are doing the MCQs of this chapter, and this is the video lecture number 2 for this series. So let's get started. All right, so the question is, the porosity of soil can be more than 100%. We have to ascertain as this statement is true or false. All right, as already discussed in the previous lecture, we have 5 very important volumetric relationships in case of a given soil sample, or in case of a given soil mass. We have 5 very important volumetric relationships. First one being the void ratio. Second one is the porosity. Third one, degree of saturation. Then we have percentage air voids. Percentage air voids. And lastly, we have air content. Right? So these are the 5 very important volumetric relationships in case of a given soil sample or a soil mass, which we know that soil, this is generally a 3-phase system, but under some special conditions, it becomes a 2-phase system. All right. So let's get back to the question. The porosity of the soil can be more than 100%. All right. Now let's quickly study what is porosity. We have already discussed in the previous chapter, but I am repeating it once again. Porosity, it is denoted by N, and it's defined as the ratio of volume of voids to the total volume in a given soil sample. All right, porosity is a ratio between volume of voids to the total volume in a given soil sample. All right, but since the volume of the voids can never exceed the total volume of voids can never exceed the total volume, therefore porosity must always be less than 100%. All right, because porosity, it is defined as a ratio between volume of voids to the total volume in a given soil sample, and this porosity, it cannot exceed 100% because it would mean that the volume of voids is greater than the total volume, which is absurd. In a given soil sample or a soil mass, the volume of voids can never exceed the total volume, which is absurd. In fact, it will have a much smaller value. All right. Therefore, porosity, which is also known as percentage voids, porosity is also known as the percentage voids, and it can never exceed 100%. All right, because in that condition, it would mean that the volume of voids is greater than the total volume in a given soil sample, which is absurd. All right, so its value will be less than 100%. And the typical porosity values, I'll write it here. Typical porosity values for certain soil types are, like for example, for dense sands, since we already know that porosity, it is generally expressed as percentage. For dense sands, its value is 25 to 40%. For clays, its value, it ranges between 40 to 70%. And third, for very loose or organic soils, the values of porosity can be high, but it can never exceed 100%. All right. So this statement, the porosity of soil can be more than 100%, is absolutely wrong. All right, because porosity is defined by N. It's a ratio between volume of voids to the total volume in a given soil sample, and the volume of voids can never be greater than the total volume, because otherwise it's an absurd statement. How can we say that the volume of the voids will exceed the total volume in a given soil sample or a soil mass? So this statement would be completely absurd. That means the values of porosity can never exceed 100%. All right, and I already shown here that some of the values for certain types of soils, like for dense sands, it ranges between 25 to 40%. For clays, it may be between 40 to 70%. For very loose or organic soils, it may be the value of percentage voids or porosity, it may be quite high, but in no case it can exceed 100%. All right, moving on to the next question. Next question is path specific gravity. All right, question is, the specific gravity of particles of coarse grained soils is seldom greater than 2.70. All right, so we have to see whether this statement is true or false. Specific gravity of particles of coarse grained soil is seldom greater than 2.70. All right, specific gravity, it is denoted by G, and it is equal to, it is also a ratio between mass density of soil solids to the mass density of an equal volume of water at 4 degrees centigrade. All right, specific gravity is also a ratio. It is denoted by G, and it's a ratio between mass density of soil solids to the mass density of an equal volume of water at 4 degrees centigrade. All right, and we also know that this mass density of water generally at 4 degrees centigrade, as already discussed in the previous video lecture, it is about 1000 kilogram per cubic meter, or 1 gram per milliliter, or it can also be 1 milligram per cubic meter. All right, now coming back to the question says the specific gravity of particles of coarse grained soil is seldom greater than 2.70. All right, the specific gravity of soil solids for most coarse grained soils, that is sands and gravels, let me write it over here. Let me rub it first. All right, so this was what actually specific gravity is. All right, so coming back to the question, the specific gravity of soil solids for most coarse grained soils soil solids rather, that is sands and gravels, they are composed of mainly quartz and similar minerals. These are composed of which minerals? Mainly quartz and similar minerals, whose specific gravity generally lies between 2.60 to 2.70. All right, the value greater than 2.70 is uncommon or seldom, we can say. Value will exceed 2.70. No, that is quite uncommon, and usually indicates the presence of heavier minerals such as iron bearing minerals. All right, if the value will exceed 2.70, it is an indication that there is a presence of heavier minerals like iron bearing minerals, like in magnetite, etc. All right, so the specific gravity of soil solids for most coarse grained soils, that is sands and gravels, they are composed mainly of quartz and other similar minerals, whose specific gravity values, they generally lie between 2.60 to 2.70. All right, and the values greater than 2.70, they are uncommon. We seldom can encounter such particles in coarse grained soils where we can see that the specific gravity will exceed 2.70. Or if certain this case happens, we find that the specific gravity of the soil minerals is exceeding 2.70, then that is definitely the presence of that soil has some minerals which bear iron. That's why their specific gravity would exceed 2.70. Otherwise, commonly or regularly, we find that the coarse grained soils such as sands and gravels, their specific gravity value generally lie between 2.60 to 2.70. All right. So coming back to the statement, the specific gravity of particles of coarse grained soils is seldom greater than 2.70 is absolutely correct. The correct range of the specific gravity for coarse grained soil particles, soil solids, is 2.60 to 2.70. All right. And if the value exceeds 2.70, then that is the indication, that is definitely an indication that there is a presence of heavier minerals like those of iron bearing minerals in that soil sample. All right, moving on. Next one. All right. The statement is the submerged density is about 1/2 of the saturated density. All right. Let's come to this statement. It says that the submerged density is 1/2 of the saturated density. First, we'll study what these are. Let us study first saturated density, all right, and then the submerged one. All right, the saturated mass density, denoted by this, is the bulk mass density of the soil when it's fully saturated. So this will be a ratio. All right, the saturated density is the bulk mass density of the soil when it's fully saturated, when there is no air phase. All right, in that case the bulk mass density becomes the saturated mass density. All right, and the submerged density these are the volume mass relationships, and we have important volume mass relationships. The first one being, let me write it over here first. We have some very important volume mass relationships in a soil sample, and some of them are the bulk mass density, and you must know that these volume mass relationships are in terms of mass density. Very important. There are other volume weight relationships also, which we'll study later. All right. So there are volume mass relationships, there are volume weight relationships. Volume mass relationships are in terms of mass density, and volume weight relationships, they are in terms of unit weights. All right, they are in terms of unit weights, and these are in terms of mass density. We have some important one like that of bulk mass density. Then we have saturated mass density or saturated density. We have dry mass density also, dry density. We have submerged mass density. All right. Now we have to study, or we have to rather ascertain the fact that whether this statement, the submerged density is about 1/2 of the saturated density, whether this is true or false. Let me rub it first. We already studied that the saturated density is the bulk mass density of the soil when it's fully saturated. All right. That means there is no air phase or the air voids are nil. In that condition, soil becomes a two-phase system consisting only of soil solids and the volume of water which will be filling its voids. All right, so submerged density. Submerged density, these are the important volume mass relationships. Submerged density, when the soil exists below water, we can say that it is in submerged condition. And when volume of soil is submerged in water, it displays equal amount of water, or we can say that it displays equal volume of water when it lies or exists below the water. So the net mass of the soil in these submerged conditions, as already discussed in the previous video lecture, is reduced, and this density, submerged density, it will become, all right, the submerged mass density denoted by this, it is defined as the submerged mass per unit total volume. It is defined as the submerged mass per unit total volume in a given soil sample. All right, and it is true that this submerged mass density is roughly 1/2 of the saturated density. This is the relation between submerged and the saturated mass density in case of a given soil sample, and it's absolutely correct that the submerged density is roughly 1/2 of the saturated density. All right, why so? Because when the soil exists below water, it is in submerged condition, and the net mass of the soil when submerged is reduced because of the Archimedes principle already discussed in the previous video lecture. So the statement, the submerged density is about 1/2 of the saturated density, is correct, absolutely correct. All right, so this statement is correct. All right, moving on to the next one, and I may also tell you that, let me drop it first, that some typical values of these densities in soil mass or a soil sample. All right, some typical values for a typical saturated soil. That is very important because we are dealing with saturated mass density and the submerged one. For a typical saturated soil, saturated density, if it would be, let's suppose, 20 kilonewton per cubic meter, then the submerged density will be 10 kilonewton per cubic meter. All right. That means the statement, because we know that this, just we studied the relationship mass density of water, we know it is 1000 kilograms per cubic meter or 1 gram per milliliter. All right, so this is the typical range of the values between saturated density and the submerged density. All right, because in terms of unit weight, if we'll take this density, it will become 10 kilonewtons per cubic meter. How so? Because if we'll take this is in terms of density, in terms of unit weight, this will be 1000 into 9.81. All right, in terms of unit weight, it will be 9810 Newton per cubic meter, which will be equal to, let me write it over here, 9.81 kilonewton per cubic meter, which is approximately 10 kilonewtons per cubic meter unit weight of water. All right, approximately equal to 10 kilonewton per cubic meter. So if we'll go on substituting the values over here, all right, then that means submerged density is equal to 20 kilonewton per cubic meter minus, in terms of, don't get confused students, I can also write it over. Just let me erase this expression. Let me convert this volume mass relationship into the volume weight relationship, and let me write it like so, that the all right, so this is the same expression, but this time this is between, in terms of unit weights, all right, not in terms of mass densities. So submerged unit weight or density will be saturated, how much, 20 kilonewton per cubic meter minus, just arrived at this, unit weight of water. So this will be equal to 10 kilonewton per cubic meter. All right. So the statement, the submerged density is about half of the saturated density, is absolutely correct. All right. Moving on to the next one. This was something about the very important volume mass relationships and the volume weight relationships in a given soil mass. All right. Whereas the volume mass relationships, they are in terms of the mass density, and volume weight relationships, they are in terms of unit weights. Right. All right. This is about the determination of the water content in a soil sample, and the statement is, for determination of water content of all types of soils, the oven temperature is 100 degrees Celsius plus minus 5 degrees Celsius. All right. The statement is, for determination of water content of all types of soils, the oven temperature is 100 degrees centigrade plus minus 5 degrees centigrade. This statement is absolutely incorrect. Why so? The soil sample in the container, for most of the soils, the temperature is between 110 degree plus minus 5 degrees centigrade. All right. And the soil sample in oven drying method, for the determination of water content, the soil sample is placed in the container, is then dried in the oven at a temperature of sorry at the temperature of 110 degree plus minus 5 degrees centigrade for 24 hours. And this temperature range selected is suitable. This is suitable for most of the soils, but not for all of the soils. This is suitable for most of the soils, as the temperature lower than 110 degree plus minus 5 degrees centigrade may not cause complete evaporation. All right. It may not cause the complete evaporation of water. And if we select the temperature higher than this range, then that will result, all right, breaking down, that may result in the breaking down of the crystalline structure of the soil particles and the subsequent loss of chemically bound structural water. All right. First, we are studying the range for most of the soils. During the oven drying method, for the determination of the water content of a soil sample, the soil sample in the container is dried in an oven at a temperature of 110 degrees centigrade plus minus 5 degrees centigrade. for 24 hours. All right. This range selected is suitable for most of the soils. If the temperature lower than 110 degree plus minus 5 degrees centigrade is selected, it may not cause the complete evaporation of water, and the temperature higher than the temperature range as selected for most of the soils, it may result in the breaking down of the crystalline structure of the soil particles and the loss of chemically bound structural water. So that means this range, the range between 110 degrees centigrade plus minus 5 degrees centigrade, is quite suitable, good enough for most of the soils, but not for all of the soils. Now we'll study some important and special cases that where we cannot select such a temperature range for oven drying of a soil sample for its determination of water content. All right, this was about most of the soils that we select the temperature range between 110 degree plus minus 5 degrees centigrade, as this is apt for most of the soils. A temperature higher than this, if selected, may cause the breaking down of the crystalline structure of the soil particles and the loss of chemically bound structural water. And if we'll select a temperature less than that, then it may not cause the complete evaporation of the water which that soil sample must be having, and will not get the correct values of the water content in that soil sample. All right, now coming to the some special cases that where we cannot select this range. For certain soils like that which contain gypsum, soils containing gypsum or other minerals which have loosely bound water of hydration, such a temperature range does not give reliable results for the water content in those soils. No reliable results. All right. So this temperature range, if we select this for the soils containing gypsum or other minerals which are having loosely bound water of hydration, it will not give us the suitable or the reliable results. And this temperature range of 110 degree plus minus 5 degrees centigrade, it's also not suitable for the soils containing significant amount of organic matter. For those soils which contain significant amount of organic matter, this temperature range is also not suitable. For all such soils, a temperature of 60 degrees centigrade to 80 degrees centigrade is recommended. All right, because at higher temperatures, why this gypsum, it has very loosely bound water of hydration, it will lose its water of crystalline, and the organic soils which contain significant amount of organic matter, they tend to decompose and get oxidized. They tend to decompose and get oxidized. All right, so this temperature range of 110 degrees centigrade plus minus 5 degrees centigrade does not give reliable results for the soils containing gypsum or other minerals which are having loosely bound water of hydration. And this is also not suitable, this range is also not suitable for all those soils which contain significant amount of organic matter. For all such soils, a temperature range usually that is which can give us reliable results, that is the range between 60 degrees centigrade to 80 degrees centigrade. This is generally recommended. Why? Because at high temperature, if we'll go on testing for oven drying method for the determination of the water content for those soils containing gypsum at a temperature of 110 degree plus minus 5 degrees centigrade, at this temperature gypsum will lose its water of crystalline, and the organic soils, they will tend to decompose and get oxidized. All right, so the statement for determination of water content of all types of soils, the oven temperature is 110 degrees centigrade plus minus 5 degrees centigrade. It's absolutely incorrect. All right. First, here also, it should have been 110 degrees centigrade rather than 100. All right. Because we just studied about the soils. For most of the soils, this oven drying method do happen for 24 hours in oven at the temperature of 110 degrees centigrade plus minus 5 degrees centigrade for most of the soils. That is true, absolutely true, but not for the soils which contain gypsum and not for the soils which have high amount of organic matter in them. All right, I hope you understood it well. So the statement is absolutely false. All right, moving on to the next one. All right. The statement is the void ratio of the saturated soil can be determined from its water content. All right. The void ratio of a saturated soil can be determined from its water content. All right. Void ratio, as already studied in the previous video lecture, is very important volumetric relationship. In case of a soil sample, void ratio denoted by E, it's defined as the ratio between volume of voids to the total volume of solids in a given soil sample. The ratio between volume of voids to the volume of solids, this term is denoted by E and it's known as the void ratio. All right. So now the statement is the void ratio of a saturated soil can be determined from its water content. This statement is absolutely correct. How so? Because for a saturated soil, the degree of saturation is For a saturated soil, the degree of saturation is 100%. Why so? Because the degree of saturation is a ratio. It's also a ratio between volume of water to the volume of voids. All right. So when the soil is saturated, the degree of saturation is 100%. The degree of the saturation will be 100% when the soil will be fully saturated, because there will be no air phase and the volume of water will be equal to the volume of voids. Because there will be no air phase in the voids, the soil will be fully saturated, and the degree of saturation, which is generally expressed as a percentage, will be 100%. And when it will be 0, when the soil is absolutely dry, there is no water in the voids. All right. So for a saturated soil, the degree of saturation is 100%. All right. And we know the expression ES is equal to WG. This is the general expression in a soil mass, and it relates certain things like that of the void ratio, degree of saturation, water content, and specific gravity. All right. So when S for a saturated soil, degree of saturation is 100%, that means S will be 1. So E is equal to WG. Since G can be determined separately, specific gravity can be determined separately, and S, degree of saturation, is 1 for a saturated soil, the void ratio can be determined from the water content. For that, we definitely need this also, the specific gravity, but that can be determined separately. All right. So the statement, the void ratio of the saturated soil can be determined from its water content, is absolutely correct. Moving on.